Hello, YouTube. I'm Dr. Paul Kerstetter, and today I would like to talk about bit alignment methods for analog to digital converters interface to FPGAs. In this video, we'll cover a feature known as bit slipping for the ISERDESE2 primitive used in Xilinx Series 7 FPGAs. I'll show you a working Vivado project and demonstrate how bit slipping works in practice. There's a link in the description for the code used in this project. Serial stream bit alignment in FPGAs. The alignment problem. Let's start by looking at the alignment problem that often arises when interfacing ADCs to FPGAs. The issue is simple. If there's a serial data stream coming from an ADC and it's captured by a deserializer into a parallel register, how does the deserializer know where the beginning of each data word is? If the ADC outputs 8-bit words, the deserializer might capture 4 bits from one word and 4 bits from the next, resulting in garbage data in the parallel register. Two ways to align the data. There are two ways to solve this problem. When the input data changes rapidly, comparable to the ADC sample rate, you'll need a frame sync signal to properly align the deserializer to the word boundary in the ADC serial stream. This relationship is shown in the diagram. When the ADC input signal changes slowly compared to the ADC sample clock and no frame sync signal is available, you're in luck. You can use bit slipping to align your deserializer so that the parallel 8-bit register captures the correct data. This video focuses on the second case, using bit slipping for alignment. What is bit slipping? So what exactly is bit slipping? Bit slipping is a method of aligning to the correct word boundary by barrel shifting the captured bits until the parallel output matches the expected value. When I first learned about bit slipping, I didn't think it could possibly work for an ADC serial stream. But then I had a eureka moment. For bit slipping to work, the analog input to the ADC must change slowly compared to the sample rate. Let's see why. A simple example. Consider the case shown in the diagram. Suppose we have a 1-second ramp input to an 8-bit ADC running at 125 MHz. The ramp repeats once per second, extremely slow to the 125 MHz sample rate. When the ramp reaches 1/4 of full scale, the ADC outputs 01000000 or 64 in decimal. Now what's the next sample value? Still 64. It hasn't changed yet. Because of the ADC's 8-bit resolution, it will take 977 more samples before the output increases to 65, or 01000001. That means the serial data remains almost constant for many clock cycles, and this stability allows the bit slip method to work effectively. How bit slipping works. Let's look at how this works in detail. Suppose we have a serial stream containing two ADC samples, each 8 bits wide. The first sample equals 64 and the second sample equals 65. In this case, the ADC input signal has been sped up, so there is a 1-bit change per sample. If the deserializer is misaligned, it might grab 4 bits from the first sample and 4 bits from the second sample. The resulting parallel output could be something meaningless, for example 20 in decimal. But if we barrel shift the 8 bits 5 times, the output becomes 65, matching the second ADC sample. That shifting process is the bit alignment in action. It works even though the two words overlap. Again, only because the analog input changes slowly to the ADC sample clock. ISERDESE2 overview. Before we move on to the Vivado demonstration, let's quickly review how the ISERDESE2 works. From the diagram, serial data from the ADC is shifted into the serial shift register. After 8 bits have been shifted in by the serial clock, the parallel register captures the data using a slower clock, a divide by 8 clock for SDR, or divide by 4 clock for DDR mode. Timing considerations. The timing diagram shows how the clocks and signals relate. The rising edge of the serial clock aligns with the rising edge of the divided clock, which corresponds to an edge of the serial data. Reset must be released between the falling and rising edges of the divided clock. The parallel register updates on each rising edge of the divided clock. The serial data is captured on the serial clock, starting near the falling edge of the divided clock. Remember, the serial data stream is least significant bit first into the deserializer. Vivado demonstration. Now that we've covered the theory and timing, let's switch over to Vivado and see bit slipping in action. This is the Vivado demonstration. In my sources view, by the way, these VHDL files are available online and they can be accessed in the link in the description on GitHub. This is my top level module, ISERDESE 8-bit DDR. Let's open that. Let's give a full screen to that. We have the entity at the top. There's a clock and a clock bar or complement clock as inputs. That's the serial clock. There's a divided clock, which is the parallel capture clock. There's a data in, which is the serial data coming in. There's a reset and there's a Q, which is the parallel capture register. This is the ISERDESE2 primitive. It's set up for DDR mode or double data rate. It's expecting a 8-bit data width. It's in networking mode, which means it's for simple serial to parallel data transfer. The Q1 through Q8 is the parallel register in which the serial stream data gets captured in. And that's about all I want to say about the ISERDESE2 primitive. Down here, I have my bit slipping process. And the way you control how much this primitive bit slips is simply by adjusting this 0. If you wanted to bit slip 1 time, you put it to 1. If you wanted to bit slip for 2 times, you put it to 2. But for now, let's keep it at 0. Bit slip, by the way, is available on the ISERDESE2 primitive right here in this statement right here. So that's for bit alignment. Now let's go to sources and open the simulation test bench, which is right there. Let's expand it to full screen. In the simulation test bench, I have serial data set up. It's going to be A5, A6, A7, A8. That's the serial data, and that's what we should see captured in our parallel register, our 8-bit parallel register. We have a clock entity. Actually, this is my top level module entity. Here's the clock process, and we are set up for 500 megahertz clock, and the divide by clock is 125. There's a ratio of 4 since it's double data rate. And then down here we have the serial data process, and I control the alignment of the serial data by setting this wait for statement to 15 nanoseconds. So we are just going to run this test bench. Make sure everything's saved. We're just going to run this test bench and see what the let's see if our serial data is captured by our parallel 8-bit register correctly. Okay, let's expand the waveforms. Let's zoom in on the waveforms and just a quick overview of the waveforms. Let's expand this window so you can see the labels. These two signals are the serial clock and the serial clock complement. This is the divide by clock. Remember, there's a divide by 4 ratio between the serial clock and the divide by clock. Here you'll have the serial data coming in. Let's move over a little bit so you can see it all. So this is all the serial data that's coming in. There's a reset, and then there's the parallel register, which is 8 bits. And if you remember in our test bench, we had A5, A6, A7, and A8 from our serial data, and that's ending up in our parallel 8-bit register correctly. So what happens if I delay this serial data relative to the clocks? Let's delay it a little bit. I'm going to go to the test bench. I'm going to set the delay from 15 nanoseconds to 17 nanoseconds. And then we are going to run the simulation again to see what happens. Okay, let's expand the window for the waveforms. And as you can see, now that our serial data came in a little bit delayed, our parallel register, it doesn't have the correct data in it anymore. And that's because the deserializer doesn't know where the word boundary is on the serial data. So I have 94, 9A, 9A, A2, FE instead of A5, A6, A7, A8. So to fix that, what we're going to do is go to the top level VHDL module, and we're going to do some bit slipping. We're going to set the bit slip, we're going to slip it 2 times, set that to a 2, but first before we do that, let's go back to the waveform window. And as you can see, this is the bit slip label. And as you can see, bit slip is low. So right now we're not bit slipping at all, but let's run our simulation where we set the bit slip to 2 and see what happens. Okay, let's expand the waveform window. Let's zoom in on the parallel data. Okay, so this is much better now. So we got our first sample in, and it came out to be 2.8, but it's probably taking its time to barrel shift to get to get to the right alignment, because now our next data is A6, A7, A8. And if you remember, that's what our serial data is. Our serial data is A5, A6, A7, A8. So we didn't get the very first sample correct, but we got the rest of the samples correct. And that just shows that it takes some time for the barrel shift operation to occur. And there's our barrel shifts or our bit slips signal. Once again, let me expand this so you can see the labels on the signals. So there's bit slip, and it's aligned with the divided clock 1. There's 1 bit slip, and there's 2 bit slip. Okay, well, that's the end of the demonstration. I hope you liked this video. If you like this video, please subscribe and hit the like button. And stay safe, and I'll see you in the next video.